Quantum entanglement is a fascinating phenomenon, but we still do not know for sure, is it local or non-local? In theory, this should be a simple question. Correlated events appear inseparable, as if they depend on each other, but sometimes we can explain this with a prior common cause. So, if quantum correlations can be conditionally independent, then we can have local behavior. If not, then quantum behavior is non-local. To make progress on this topic, John Bell came up with the following theorem. However, Bell's argument cannot answer questions about locality on its own. To bridge the gap between theory and interpretation, it requires the following criterion. If a quantum wave function is physically inseparable, then the corresponding events are statistically inseparable. And so the question becomes, is Bell's criterion justified? The goal of the current presentation is to clarify the relevant concepts and to advance this debate with an experimental counterexample to Bell's locality criterion. A known feature of entangled quanta is that they have correlated properties. In the case of polarization entangled photons, this can happen in two ways: either both twins have the same state of polarization, or they are orthogonally polarized. In a type 1 experiment with entangled photons, Alice and Bob can make identical measurements and always obtain identical results. If Alice 1 transmits or reflects a photon, then Bob 1 does the same, and vice versa. To complete the experimental setup, we add two more polarizing beam splitters, one in each path. Again, Alice 2 and Bob 2 are set to make identical measurements at some fixed angle from Alice 1 and Bob 1. The first thing to notice here is that our experiment is local. Alice 1 and Bob 1 make identical measurements and obtain identical results. This is not problematic. Likewise, Alice 2 is downstream from Alice 1. Therefore, it is also independent from Bob 1 and Bob 2. Every event in this experiment will be the same as one can expect in classical physics. The second thing to notice is that consecutive measurements of polarization obey Malus' law. Therefore, they can violate the Bell inequalities. However, diagonal correlations across the paths are identical to the correlations between consecutive measurements. Therefore, coincidences between Alice 1 and Bob 2 must also violate the Bell inequalities. To sum up, we have a straightforward demonstration that Bell violations are possible for independent observables. So, what is going on? Let us recall that this debate started with the EPR paradox. According to that argument, we have to treat quantum observables as if they are real prior to the act of measurement. In other words, we have to treat quantum observables as if they are symbols that are printed on playing cards before we shuffle them. And so, we should be able to explain their correlations in terms of conditionally independent pre-existing properties. However, such correlations cannot violate Bell's inequality. Therefore, Bell experiments do not reveal pre-existing properties. Indeed, this is what we see in our experiment. When a photon is transmitted at Alice 1, it is vertically polarized. Then, Alice 2 will absorb this polarization and transmit or reflect a different state. In short, measuring polarization is like twisting a rubber band. We can do it clockwise or counterclockwise, but we can only do one transformation at a time. More importantly, we do not reveal pre-existing properties. The twisted state cannot be real prior to the applied torsion. Surprisingly, these transformations can be conditionally independent and still violate the Bell inequalities. The reason for this feature is that non-commuting properties exist only one at a time. Therefore, they cannot constrain each other statistically like properties that exist at the same time. According to Bell, physical separability equals statistical separability. However, the structure of the wave function is irrelevant if we transform the wave function as a whole. In conclusion, Bell's locality criterion cannot be correct because it has an experimental counterexample.